Hi, in this video we are going to talk about level order traversal or breadth first search of binary tree. We are given a binary tree, we need to print all nodes of it in level order fashion. We begin with the root, we print it, then we print the nodes at next level. You can draw the lines like this and you can simply print nodes from top line to bottom line. So you print 10 first, then you print 20, 30, then you print 8, 7, 6 in the same order from left to right. Then you print 9, 5, 9, 15. So output is 10, 20, 30, 8, 7, 6, 9, 15. For this tree, there are 3 lines. You will print the top line nodes first, then second line, then third line. 3, 4, 5. In this tree, you will print this node, then this node, then these 2 nodes, then this node. So your output is going to be 8, 6, 2, 4 and 3. Now please pause this video and try to think of a solution that prints level order traversal and try to implement it. One simple solution to print level order traversal of a binary tree is you use 2 functions that we have discussed in the previous videos. One function to find the height of binary tree, the other function to print nodes at distance k from the root. First you find out height of binary tree, right? For this tree you are going to get the height as 1, 2, 3, 4, right? So you know that you need to print 4 levels. And how do you print the individual levels? You have another function that prints all the nodes at distance k from root. So you call this function first for k equal to 0 so that you print the root. Then you call this function again with k equal to 1. Then you call this function again with k equal to 2. So this way you get all the nodes printed of this tree. You may refer the videos of height function and the functions to print nodes at distance k from the root. We can simply use those functions to print the level order traversal. But this solution is definitely inefficient. You will need big O of n time first to find the height. Then if the height is h, then you are going to run a loop which is theta h, and inside this loop you are going to call a function which is big O of n. So your time complexity is going to be n plus h into n, and your overall time complexity turns out to be big O of h into n. We can print level order traversal in big O of n time. Now how do we print level order traversal in big O of n time? Suppose I begin from the root and say I try writing some recursive function, I go to the left subtree, then how do I come back to this node just after printing this particular node? But when you call for recursion, what will happen? This recursion will first finish this subtree. How do I bring the control back to this node just after printing 20? So recursion is not a good idea here. We need to use queue data structure. Please pause this video again and try to use a queue data structure to print the level order traversal. Let us now talk about implementation and algorithm. The idea is this: you enqueue a level into the queue, then you take out these items from the queue and print them on the screen, and when you are taking out an item, you enqueue the children of it, which means you enqueue the next level. So first you enqueue the root, which is your first level. You take out the root, you print it, and then you enqueue its children. So your second level goes into the queue. And when you are taking out the second level nodes, you enqueue the third level nodes into the queue. And when you are taking out third level nodes one by one, you enqueue the fourth level nodes into the queue. So this way, your queue prints the items in level order, because queue is first in, first out. You are taking in root, you will take out root first. And when you take out root, you will enqueue its children. So when you take out its children, you will enqueue their children, which means next level into the queue. So when you are taking out the current level and printing it, you are also enqueuing the next level. That is how you get the level order traversal. Let's see under this step by step. So what are we doing in this? We first create an empty queue, as you can see in both the codes. Then you are enqueuing root into the queue. Then you are running a loop while queue is not empty. And what are you doing inside the loop? You are taking out an item, then you are checking whether its left child and right child are not empty. If they are not empty, then you are enqueuing them also into the queue, right? And then you again take out an item and you print that item also, to print the items in level order traversal. So there are three states of every node. First state is it never went into the queue. The second state is it's there in the queue, and third state is it went into the queue and it came out of the queue, right? Every node always goes through all the three steps. Initially, when your queue is empty, all the nodes are in undiscovered state. They never went into the queue. Then you enqueue the root, so it goes into the queue, and this state is called discovered. This node has been discovered. Then when you take it out of the queue, the third stage it has been processed, it has been printed. So when you print the root, it is processed, and then you enqueue its children. So they go from undiscovered state to discovered state. So we first create an empty queue, then we enqueue the root. Here and here we first add root to the queue. Then we run a loop while queue is not empty, and inside this loop we take out an item. So we take out 10 and we print it on the screen, right? So we print 10 on the screen. Now after printing 10, we will enqueue its children. So we will have 15 and 20 into the queue. Right, now we'll take out 15 and enqueue its children. So you'll print 15 and you will enqueue its children. 30 will be enqueued. Now you will take out 20 and you will enqueue its children. So you will have 40 and 50 into the queue. 30, 40, 50. Next time you will take out 30 from the queue and you will print 30. And there are no children of 30, so you will not enqueue anything. And after that you will take out 40 and enqueue 60 and 70 into the queue. And after that you will take out 50 and you will not enqueue anything. So your queue will have then 60 and 70. Then you will take out 60 and 70 also one by one and you will print them. What is the time complexity of this solution? If you take a closer look at it, you can notice every node goes into the queue exactly once. It comes out of the queue exactly once. So that is what happens throughout this process. All the nodes one by one go into the queue, and all the nodes one by one come out of the queue. Now what is the time complexity of enqueue operation? Enqueue operation on a queue is always big O of 1. And what is the time complexity of dequeue operation? Dequeue operation is also big O of 1. So you are doing big O of 1 work for every node. That is how the time complexity of this overall solution is big O of n. Let us now talk about time complexity and auxiliary space in detail. I just discussed that for every node we do big O of 1 work, which is enqueue and dequeue. So the time complexity I mentioned as big O of n. If we want to be more precise, we can say time complexity is theta of n, because for n nodes it's always going to do enqueue dequeue for every node. So theta n is a better expression for time complexity. Now what is the auxiliary space requirement? Auxiliary space requirement is big O of n. Here I am using big O because sometimes the auxiliary space is going to be constant and sometimes it's going to be theta n. Auxiliary space is equal to the queue size. Now how big queue you need? One interesting fact about level order traversal is, in queue you will have at most one level at a time. When you process the first level, which is root, you have the next level into the queue. When you process the last item of next level, you have next to next level into the queue. So you will have one level at most at a time. So if we want to be doing exact analysis, we can say auxiliary space is equal to width of binary tree. Like in recursive traversals or depth first search traversals, your auxiliary space is height of binary tree, here it's width. So if your tree is skewed, your auxiliary space is going to be theta 1. If your tree is perfectly balanced like this, then auxiliary space is going to be theta n, because the width of this binary tree, which is the number of nodes in any level, is equal to n by 2. You see the last level. How many nodes this tree has? This tree has 15 nodes, and out of these 15 nodes, half nodes are here, more than half. 8 nodes are there, 15 plus 1 by 2. That's what happens in a perfect binary tree when it's perfectly balanced. You have n by 2 nodes, n plus 1 by 2 nodes at the last level. So in this case, the auxiliary space is going to be theta n. So in general, we can say that auxiliary space requirement for level order traversal of binary tree is theta of W, where W is width of binary tree, and this W can go up to n, it can be 1 also. So we can, if you want to use big O notation, then we can say big O n, but if you want to use theta, if you want to be accurate, we can say it's theta W, where W is width.